What I really want to do too is to put some really basic things in front of you. Bulk and particularly bulk density is a component of the soil characteristics that we're talking about. What is it? Why is it important? How do you measure it? Some tricks and traps and uses. Now this is a joint talk with Brian Murphy and myself. Brian's above me here because Brian's the organ grinder and I'm the organ grinder monkey. So we'll see how we go. Bulk density, what is it? Well, simply the mass of oven dry soil per unit volume. There are a few tricks in here, but for instance, under normal soil conditions, it's oven dry. If it's a highly organic soil, you're probably a bit concerned about taking to oven dry mass. You see the bottom part of that equation, total volume of soil. Oh, incident, all this is available, so you don't have to sort of take in all these equations, even though they're pretty straightforward. So the volume of soil is equal to the volume of the air plus the volume of water plus the volume of solids. And the units are numerically equivalent, be it grams per cubic centimetre or tonnes per cubic metre or megagrams per 10 to the 6 grams per cubic metre. Normal range, typically 1.1 to 1.8. 1.1 could be quite a fair amount of organic soil. 1.8 you're starting getting some compacted soil that feel more like concrete. You can get soil down to about 0.5 if it's a highly organic soil, and up to 2 if you've got, say, a sodic subsoil. The normal range is that. Why we measure it? Well, because there's a major determinant of soil characteristics, one of which is soil porosity. Soil porosity is really simply 1 minus the bulk density divided by the particle density. Example, if the soil's got a bulk density of 1.4, you notice I'm not using units because I've talked about before they're numerically equivalent. So it's 1.4, a specific gravity in quartz, 2.65. If you've got a soil that's got other materials in a heavy mineral soil, you may have a higher number than 2.65. Soil porosity is simply 1 minus 1.4 and 2.65, straightforward equation, times 100, gives you 46%. Sorry, 47%. Volumetric moisture is simply the volume of water over the volume of the total volume of the material you've got in front of you. Whilst airfill porosity, and the reason I'm doing it is just so that it sets the scene. Airfill porosity is simply the soil porosity minus the volumetric moisture content. One of the critical things in this is to say that numerical soils have an airfill porosity of less than 10% round fill capacity, and that's a general sort of term, but if you're getting that sort of airfill porosity at the soil, the moisture content you'd like to have a lot of growth in, you've got problems because the soil's basically going into waterlogged and you've got a very small available water content in that particular soil. Why is bulk density important? Well, I don't know if I have 3 things here. One is an indicator the extension of compaction, and therefore if the roots can't get through it, you've got reduced root penetration ability, so reduce exploration and use of the soil resources. The second thing is that the bulk density is an influence of the soil hydraulic conductivity via compaction. The third one is, I mentioned this airfill porosity at fill capacity. If you have a high bulk density, you've got a greater risk of waterlogging and therefore a greater risk of root death unless you're growing rice. The importance or the key areas of when bulk density become really important depend very much on the soil structure, the soil texture. So if you've got sandy soil, you can get down to maybe at 1.6 units. In loams, it's about 1.4, and in clays from about 1.2 onwards. Now, most agricultural soils, in particular clays, are about 1.4 to 1.6, and you throw a barbecue if you had 1.4, you're going really well. And yet it's starting to get into problems with compaction. What's the actual effect of this compaction? This particular soil photo I took up on the Bowley Plain north of Townsville a few months ago. The key point in this here is that we've got about 10 to 15 centimetres of topsoil, and we've always got this layer of concrete below it. And what does that do to the roots? The roots can get down to here, and they stop. They can't go any further. You get a lot of horizontal movement of roots in that soil, very few roots into the subsoil. So that you're expecting plants, you say, oh, I've got 2 metres of soil there. In fact, you've got 20 centimetres of soil if you're lucky. So that's a major impediment to plant growth, as you can see. There are other reasons for this type of thing. For instance, if you're going to an acid sulphate soil and the pH is 3 down here, you probably get your roots starting to do something like that. If it's a plough pan, if that's been ploughed for 100 years and it's just compacted down. But in this case, it's this issue of bulk density in the subsoil. Thanks. 5. Okay, good. Okay. What sort of sampling issues do we have when we're talking about bulk density? And this is taken from Dave Mackenzie's brother's excellent book. Core diameter, in theory, it should be at least 75 millimetres. Now, when I do it, I have a smaller one for a good reason. If I'm going down 30 centimetres and I need to have 75 mil, it's very difficult to actually get a good sample with a machine like that. The core length, according to Mackenzie, should be approximately the soil core diameter. But if you are doing a sample of, say, 30 centimetres diameter, sorry, try again. You're doing depth that suggests you have to have a soil that time. If you're doing a few hundred of those a day, you need to be double to get around the paddock. So it's got a practical issue. The other one, the final one here is optimum moisture. And somebody I think is going to be talking about the importance of field capacity and that type of thing, and also the nomenclature of field capacity. But I just want to make a point that this is the optimum one, particularly because if you're working with, say, a swelling clay soil, you've got to allow for the fact that it's going to change as the moisture changes. So you want to get something that's reasonably sensible. And I mentioned plastic limit. That's because I do a fair bit of sort of physical type of sense. The plastic limit is when you can roll the soil, the moisture which you can roll the soil like that and form something about that thickness without falling apart. And it needs to be slightly wetter than that to get the optimum moisture of the sampling. Okay, what to do if you've got large roots? And for instance, if you're working in an apricot plantation, or an orchard, or banana plantations, this type of thing like that. You've got large roots there. What are you going to do with them? Well, I would suggest you grind them, because particularly if you're looking at soil organic carbon and they're part of the system. If there's gravel in there, and sometimes you go into a gravelly soil, well, that's a real problem. If you're dealing with sort of cobbles and things like that, and your sample is the size of that, you've got a real problem getting bulk density. And there's a calculation for allowing for it. Some people prefer to leave it in, some people prefer to leave it out. I actually prefer to actually record that separately. And how do you handle swelling soils? Well, I mentioned this idea of the optimum moisture, which is around field capacity you're doing the sampling. But you have to remember that if you're dealing with swelling soils, you're dealing with a soil that's doing this to you. This is a non-swelling soil. So, as the soil moisture content goes up, your bulk density doesn't change. This makes life easy. But if you're dealing with a very strongly swelling soil, like this one here, as your moisture content falls down, your bulk density goes up. So where do you do your sampling? It's very important to make sure you quantify where you're doing the sampling, because if you need that bulk density information. One of my favourite toys is this thing. I use this for carbon sequestration, but for a lot of things. Split soil sampler, stainless steel, joins like that, screw on either end, take the 30 centimetre soil out of the ground, unscrew it. And the big advantage of this over, say, hammering a soil in probing is you can actually get a bit of an idea of what the soil structure's like. And you can also see root material and stuff like that down there. So it's a handy way of doing it. And I happen to love this instrument. Good. Okay. I just mentioned equivalent mass. I'll talk about it later. Equivalent mass is a problem that comes up if you've got compacting soil or if you're changing the bulk density of the soil. If you want to keep it constant, make sure if you're doing any work with carbon sequestration, it's quite an important thing, and we'll talk about that a bit more. Can we reduce bulk density? I said what a naughty thing it is. Can we do something about it? This is an example from some work I did in the Tweed Shire of 25 sites, and we looked at 2 years after putting some organic matter, soil organic carbon percent. In the control plots, 0.13, gain plus 0.34%, probability 98%. Bulk density, that one actually went up slightly. This certainly came down, wasn't statistically significant, 95% off. But it says, yes, you can do something about bulk density if you've got a problem with it. That's the point of that. Okay, practical tips. Very quickly. Right, one is, get landholders' involvement if you're doing manual soil sampling. Now, my mate here, he probably weighs about half this bloke, and this bloke, he sold it. He said, look, you don't have to spend any money on Jim this week if you come out and help me do the soil sampling. Good way of getting help. The other one too is that locals are often very interested in your soil sampling, and the practical tip is these animals have very, very large hooves. Just a moment, just last one. One of these ones, one of those swine, I call them a swine, come over and trod on my soil sieve. So, you know, it's a bit of a problem. Thank you.